Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will see that what is serial binary multiplier and how this circuit works. And at the later part of the video, we will also see that how to design this circuit. So previously, we have already seen that how to design the binary multiplier circuit. So basically, this circuit multiplies the two binary numbers. But this multiplier circuit is the fast multiplier because during the multiplication, this circuit adds all the partial products simultaneously. So this circuit consists of the AND gates, full adders as well as the half adders. So we can say that this multiplier circuit is the combinational circuit. And we have seen that in this circuit, for the n bit multiplication, we require the n square AND gates, n half adders and the n times n minus 2 full adders. So as you can see, as the number of bits in the multiplication increases, then the required number of hardware will also increase. And because of that, the size and the complexity of this fast multiplier will also increase. But all the applications do not require such fast multiplier. And in some applications, the same multiplication circuit can also be implemented using the sequential circuit. So this serial binary multiplier is a sequential circuit which multiplies the two numbers. So for the n bit multiplication, it requires the less hardware compared to the combinational multiplier. And in applications where we have a space constraint, such design is very useful. So first, let us see the working of the serial multiplier. And for that, first let us quickly go through using the pen and paper method how we are performing the binary multiplication. So in a binary multiplication, the one number is known as the multiplicand while the second number is known as the multiplier. So here, starting from the LSB, the each bit of the multiplier is multiplied with the multiplicand. And in this way, we will get the different partial products. So here, when the LSB B0 is multiplied with the multiplicand, then we are getting the one partial product. And here, since we have a 3 bits in the multiplier, so we will get total 3 partial products. And as you can see, during the multiplication process, as we move from the LSB towards the MSB of the multiplier, then the each partial product is left shifted by the 1 bit position. And finally, the addition of all these partial products will be the result of this multiplication. So that is how, using the pen and paper method, we are performing the binary multiplication. So here, instead of adding all the partial products together, what we can do? We can add only two partial products at a time. So the addition of these two partial products will be called as the partial sum. And the result of that addition will once again get added with the next partial product. And in this way also, we can perform the same addition. So let us take one simple example so that it will get clear to you. So here, the multiplicand is 101 while the multiplier is equal to 111. So here, when the LSB of the multiplier is multiplied with the multiplicand, then we will get the same number. That means here, the first partial product is equal to 101. So now, if we move to the next bit, then that is also equal to 1. That means now, the next partial product is also equal to 101. But now, it will get left shifted by the 1 bit. So here, what we will do? We will add these two partial products. And after the addition, this will be the partial sum. That is 1111. So now, once again, if we move to the next bit of the multiplier, then that is equal to 1. So once again, the next partial product will be equal to 101. But once again, it will get left shifted by the 1 bit position. And then after, it will get added with this partial sum. So now, after the addition, if we see the final output, then that is equal to 100,011. And in this way, we will get the final output after the multiplication. So here, every time before the addition, what we are doing? We are shifting the partial product to the left side by a 1 bit. And here, the partial sum is kept as it is. But for implementing the same thing in the hardware, it is better to shift this partial sum to the right side by a 1 bit. And it is better to keep the partial product at the fixed position. Because by doing that also, we will get the same result, right? So let us see how. So once again, let us take the same example and let us multiply the two numbers. So here initially, the partial sum will be equal to 0. And here, since we are multiplying the two 3-bit numbers, So the maximum value of the product term will be of 6 bits. And that is why here the partial sum is represented by the 6 bits. So now when the LSB of the multiplier is multiplied with the multiplicand, then the first partial product will be equal to 101. So now this 101 will be added to the partial sum starting from this location, and the result will be equal to 101000. So now this result will be shifted to the right side by a 1 bit position. So after the right shift operation at the MSB, we will have the 0, and the bit which was earlier at the LSB position will go outside. So basically here we will consider only 6 bits. So now if we move to the next bit of the multiplier, then that is also equal to 1. That means here the next partial product will be equal to 101. So once again it will get added with this partial sum, and after the addition the result will be equal to 111100. So once again now this partial sum will be right shifted by the 1 bit position, and once again this LSB will get discarded. So now if we see the next bit of the multiplier, then once again that is equal to 1. That means the next partial product is also equal to 101. So it will get added with this partial sum, and after the addition the result is equal to 100010. So once again here we will consider only 6 bits and the LSB will get discarded. Because like I said, here since we are performing the 3-bit multiplication, so after the multiplication the size of the product term can be maximum of the 6 bits. And that is why here we are considering only 6 bits. That means here during this binary multiplication process, instead of shifting the partial products to the left side by a 1 bit position, if we shift the partial sum to the right side by a 1 bit position, and if we keep the position of the partial product same, then also we can get the same result. So here for the multiplication of the two 3-bit numbers, here we have performed the add and shift operations 3 times. So here this method of the binary multiplication is known as the add and shift method. So now let us see how to implement it in the hardware. So here for multiplying the two n-bit numbers, we will require the 3 n-bit registers. Let's call them A, Q and the M, where the M is the multiplicand, Q is the multiplier and A is the accumulator. That means in this A register, the partial sum will be stored. So we know that during the multiplication, if the bit of the multiplier is 0, then the partial product will be 0. And if the bit of the multiplier is 1, then the partial product will be same as the multiplicand. So for the hardware implementation, we will compare the LSB of the multiplier. So if this Q0 bit is 0, then as you know, the partial product will be equal to 0. And in that case, this 0 will be added with this A. And if this Q0 is 1, in that case, this multiplicand will be added with this A. And once again, after the addition, the result will be stored in this A register. And once it is stored, then the right shift operation will be performed. So now, this Q0 bit, which was earlier at this LSB position, will go outside. And now, the bit at the Q1 position will come to the LSB position. So in this next iteration, this Q1 bit will be compared, and based on that, once again, either 0 or M will be added with this A register. And after the addition, once again, the right shift operation will be performed. So this process will continue until we compare all the bits of this multiplier, or in other words, until we compare all the bits of this Q register. So basically, here we will perform the add and shift operation for the n times. So that is the basic philosophy of this serial binary multiplier. So now, let us put some numbers and let us see how it will work. So let's say this Q is equal to 1010 and the M is equal to 0110. That means here, the multiplicand is equal to 0110 while the multiplier or this Q is equal to 1010. So we know that when the 10 is multiplied with the 6, then the result should be equal to 60, right? Or in the binary, that is equal to 111100. So initially, when we start the multiplication, then the C and the A register will be equal to 0. And the value of the multiplier and the multiplicand will be stored in this Q and the M registers respectively. And once that is loaded, then the multiplication process will start. So first, the LSB of the Q register will be checked. So here, since it is 0, so the 0 will be added with this A register. And the result of that will be once again stored in this A register. So after the addition, this A will remain 0. And now, the logical right shift operation will be performed on the C, A and the Q registers. So as you can see, this 1 will come over here, and similarly, the other bits will be shifted to the right side by a 1 bit position. So basically, this is the 1 add and the shift operation. So similarly, the 3 more add and shift operations will be performed. So now once again, let us check the LSB of this Q register. So now if you see, then that is equal to 1. So now this M will be added with this A register. And after the addition, the value will be once again stored in this A register. So after the addition, if we see the value of the A, then that is equal to 0110. And here, the C and the Q will remain as it is. So after the addition, once again, the C, A and the Q registers will be logically right shifted by the 1 bit position. So as you can see, after this right shift operation, this 1 will come over here, and similarly, all the bits are shifted to the right side by a 1 bit position. So that is the second add and shift operation. So here, since the Q and the M are of 4 bits, so we need to perform this add and shift operation 4 times. That means here, to get the final output, 2 more add and shift operations are remaining. So once again, now the LSB of the Q register will be checked. So now if you see, then that is equal to 0. That means now, the 0 will be added with this current value of the A register. And after the addition, the sum output will be once again stored in this A register. So after the addition, the value of the A is equal to 0011. And here, the C and the Q will remain as it is. So now, the every bit of the C, A and the Q register will be logically right shifted. And after the right shift operation, this will be the content of the C, A and the Q registers. And now, the final add and shift operation will be performed. So once again, the Q0 bit of this Q register will be checked. So now if you see, then that is equal to 1. That means now, the value of the M will be added with the current value of this A register. And after the addition, if we see the value of the A, then that is equal to 0111. So now, this value will be once again stored back in this A register, and the value of the C and Q will remain as it is. So after this addition, once again, the every bit of the C, A and the Q will be right shifted by the 1 bit position. That means now, if we see the content of the C, A and the Q registers, then that is equal to 000111100. So now, the 8 bits of this A and the Q register represents the final output after the multiplication. So basically, for multiplication of the two 4-bit numbers, we need to perform this add and shift operation 4 times. So in this example, no carry was generated during the addition. But if the carry is generated, then also the process will remain the same. So now, let us take one more example where during the add and shift operation, the carry will also get generated. So in the next example, this multiplicand is equal to 1111 while the multiplier is equal to 1110. So after the multiplication, this should be the answer, that is 210 in the decimal. So now let us see how this multiplication can be done using this add and shift method. So here initially, the C and the A will be reset to 0 and the Q0 bit of the multiplier will be checked. So here, since the Q0 is 0, so the 0 will be added with this A register, and the result of that will be once again stored in this A register. So after the addition, the value of the A will be equal to 0000, and here the value of the C and Q will remain the same. So after this addition, the each bit of the C, A and the Q registers will be right shifted by the 1 bit position. And after this shifting, this will be the content of the C, A and the Q registers. So once again, now this Q0 bit will be checked, and now if you see, then the value of the Q0 is equal to 1. So now this multiplicand will be added with the current value of this A register. And after the addition, the sum output will be once again stored back in this A register. So after that addition, once again, the right shift operation will be performed on the C, A and the Q registers. So far, we have performed the add and shift operations 2 times. So now once again for the third time, this Q0 bit will be checked. And here, since it is 1, so this multiplicand M will be added with the current value of the A registers. And after the addition, the sum output will once again get stored in this A register. So here, after the addition of this A and the M, the result is equal to 10110. So here, this carry will be stored in this C, while the remaining 4 bits will be stored in this A register. And now, the every bit of the C, A and the Q registers will be right shifted by the 1 bit position. So as you can see, now this C will come over here, and likewise all the bits will be right shifted by the 1 bit position. And here, since we are performing the logical right shift operation, so the new value of the C will be equal to 0. So now once again, if we see the value of the Q0, then that is equal to 1. That means once again, the M will be added with the current value of the A register. So if we add this A plus M, then the result is equal to 11010. So once again, the carry will be stored in this C. And once it is stored, then the C, A and the Q registers will be right shifted by the 1 bit position. So as you can see, after the shifting, this 1 will come over here. And subsequently, all the bits will be right shifted by the 1 bit position. So here, after the 4 add and shift operations, the content of this A and the Q register represents the final output. That is the multiplication of the Q and the M. And in this way, serially we can multiply the two numbers. So for the hardware implementation, let us see what we will require. So like I said, here we will require the 3 registers. That is A, Q and the M. And out of the 3 registers, this A and the Q should be shift registers, so that we can perform the logical right shift operation. And then to store this carry bit, we will also require the additional 1 flip-flop. Apart from that, to perform the addition, we will also require the AND bit adder. And here, to control the add and shift operations and to count the number of iterations, we will also require the control unit. So here, this control unit checks the Q0 bit of the Q register, and based on that, it will generate the selection input for this multiplexer. So here, if Q0 is 0, then the 0 will be selected, while if the Q0 is 1, then the M will be selected. That means one of the input to the adder is this A register itself, while the other input is the output of this multiplexer. That means here, the output of the multiplexer will be added with the current value of the A register. And then the sum output will be once again stored back in this A register itself. And during the addition, if the carry is generated, then it will be stored in this carry bit. And once this addition is performed, then the logical right shift operation will be performed. So all these add and shift operations and the number of iterations will be controlled by this control unit. That means here, the control unit will perform this add and shift operations until all the bits of these Q registers are checked. So that is the basic block diagram for the serial multiplication using this add and shift method. So now, let me show you the simulation for the same. And let me show you how actually it can be implemented. So here, this circuit is designed for the 4-bit serial multiplication. So here, these are the 3 registers, and out of them, these 2 are the CISO registers with the parallel load feature. So here, this serial in serial out operation with the parallel load is implemented using this universal shift register. So apart from that, this is the 4-bit adder circuit, and one of the input to it is the output of this A register. And if you see the another input, then that is coming from this multiplexers. So here, the 2 inputs of the multiplexer are 0 and the M. And based on the LSB of this Q register, the selection input will be decided. And accordingly, either 0 or M will be selected, and it will get added with this A register. And after the addition, the output will be stored back in the same register. And once again, the same process will be repeated until all the bits of the Q registers are checked. So here, this control circuit takes care of the everything. So if you want to know how this control circuit is designed, then I am going to cover it in one of the members only video. So you can check over there. But now, here let me just run the simulation and let me show you the output. So here, the multiplicand is set to 0011 and the multiplier is also set to 0011. So here, when we want to perform the multiplication, then the start pulse will be generated. And once that is generated, then the multiplication process will start and it will continue until 4 add and shift operations gets completed. And then the final result will be available in this A and the Q registers. So if you see the content of this A register, then that is equal to 0000. On the other hand, if you see the content of the Q, then that is equal to 1001. And in the decimal, that is equal to 9. So in this way, it is possible to implement the serial multiplier in the hardware circuit. So I hope in this video you understood what is serial binary multiplier, how it works, and how it can be implemented in the hardware. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.